Section 4.5, Probability with Permutations and Combinations, Video 2. In this video, we will cover the following objective: solve probability problems involving combinations. Suppose a person is playing a state lottery game in which 5 numbers must be chosen from 1 to 50 and the order of selection doesn't matter. What is the probability of winning this lotto if one ticket is purchased? This is an example of a probability problem involving combinations because we are selecting numbers from a group. We're assuming that we don't select a number more than one time, and the order of a selection doesn't matter. To find the probability of winning, we must find the number of combinations of 5 winning numbers from the 5 winning numbers. And then we will divide that by the total number of possible combinations of 5 numbers from a group of 50 numbers. So in the numerator, there's only going to be one way to select all 5 winning numbers, and that's to have the ticket with all 5 of those numbers. So in the numerator, we would look at the number of combinations of 5 winning numbers, and we want to select 5 of those, all 5. In the denominator, we will look at the number of combinations of 5 numbers chosen from a group of 50. So this is the number of possible combinations altogether. And in the numerator, C5, 5 is going to be 1. So there's only one way to select all 5 winning numbers, and that's to have the ticket with all 5 of those numbers. And in the denominator, we have to calculate C50, 5. That is the combination formula that was discussed previously. In this one example, I will show the formula, and then other than this, I will just show answers. So to do C50, 5, we would take 50 factorial, and we would divide that by 50 minus 5, which is 45 factorial, and then times by 5 factorial. So that would need to be worked out. And if it was to be worked out, it would end up being 2,118,760. That's the number of possible combinations if we are selecting 5 numbers from this group of 1 through 50. So our probability of winning with one ticket would be 1 out of 2,118,760. Now, if I punch that into a calculator, my calculator displays something like this: 4.7197 E negative 7. That E negative 7 is scientific notation, and every calculator, displays it a little differently. What that means, that negative 7, that means that the decimal would need to be moved 7 places to the left. That would give me this result: 2, 4, 5, 6, 4, 7, 1, 9, 7. And so that is the probability approximately as a decimal. And to turn that into a percent, we would multiply that by 100, which would give 0.000047%. So the percent chance of winning is very, very, very small. Example 3, to play a lottery, a person must select 5 unique numbers from 1 to 75 without regard to order, and 1 additional number from 1 to 25. What is the probability of winning with 25 different tickets? Again, this is a probability question involving combinations because we are selecting items from a group without regard to order. Let's first look at the probability of winning with one ticket, and then we'll talk about how to find the probability of winning with 25 tickets. So first we want to find the number of combinations involving all winning numbers. So that would be the number of combinations of 5 winning numbers from the group of 5, and then the number of combinations of 1 winning number from that second group. And we would multiply those due to the fundamental counting principle. We're going to divide that by the total number of combinations. And in order to get the total number of possible combinations, we are selecting, first of all, 5 numbers from a group from 1 to 75. So out of 75 numbers, we are selecting 5. And then we're selecting one additional number from a group of 25. And we would multiply due to the fundamental counting principle. So in the denominator, we would have C75, 5 times C25, 1. Again, this represents selecting 5 numbers from the group of 75, and this represents selecting 1 number from the group of 25 numbers. I'm not going to show the combination formulas. I will just show the results. So the numerator ends up being 1. There's only one way to select those winning numbers, and that is to have the ticket with the winning numbers. In the denominator, the C75, 5 ends up being 17,259,390. And then we're multiplying that by C25, 1, which ends up being 25. When I multiply those combinations in the denominator, I get 1 out of 431,484,750. And that ends up being the probability of winning with 1 ticket. Very small probability. Now, if we want to look at the probability of winning with 25 tickets, that means that our chances are multiplied by 25. So it'd be 25 times the probability of winning with 1 ticket. So we're 25 times more likely to win. Think about it, we'd have like 25 different chances of winning as opposed to just 1. So my probability increases by a factor of 25. So that would give 25 out of 431,484,750. This simplifies to 1 out of 17,259,390. So a very, very small probability. On a calculator, my calculator displays 5.7939 E-8. And again, that E-8 is scientific notation, which means that the decimal would have to be moved 8 places to the left, which would give this answer 7 zeros and then 57939. So that would be the decimal approximation of this probability. To get the percent chance, we would multiply that by 100, or in other words, move the decimal 2 places to the right. Example 4, suppose a person is playing a card game in which 5 cards are dealt to each player at random from a standard deck of 52 cards. What is the probability that the hand of cards consists entirely of cards that are not face cards? So first of all, let's talk about what face cards are. Face cards are jacks, queens, and kings. And there are 4 jacks, 4 queens, and 4 kings, which means that there are 12 face cards. Out of 52 cards, if we take those 12 away, that means that there are 40 cards that are not face cards. This is an example of a probability question involving combinations because we're dealing cards. No card is going to appear more than once, and the order of the cards in your hand does not matter. So we want to find the number of combinations of 5 cards taken from the 40 non-face cards. And then we want to divide that by the total number of combinations of 5 cards from the deck of 52 cards in general. Using the combination formula, we have 40 non-face cards, and we are wanting to select 5 of those. And then in the denominator, there are 52 cards in general, and we are being dealt 5 of them. Without showing the combination formulas, the numerator ends up being 658,008, and the denominator ends up being 2,598,960. So that is the probability of being dealt a 5-card hand where all of the cards are not face cards. This simplifies to 2,109 out of 8,330, which is approximately 0.253, or as a percent, 25.3%. So there's about a 25% chance that if we're randomly dealt 5 cards, that none of the cards are face cards. Example 5, a college math advisory board consists of 20 math educators and 10 college administrators. A 6-person committee is created to provide feedback on a newly proposed act. If committee members are selected at random, what is the probability that the committee consists of an equal number of educators and administrators? So in other words, if we're selecting 6 people, we would like 3 of them to be educators and 3 of them to be administrators. This is a combination problem because we're selecting people to form a committee. Order does not matter. No person is going to fill more than 1 spot. We want to find the number of combinations consisting of 3 educators from a group of 20. So 20 educators, and we're hoping to get 3. And 3 administrators from a group of 10. So we would have those combinations in the numerator. Then we would like to divide by the total number of combinations altogether. So if we combine all of these people into one group, altogether we have 30 people, 20 math educators and 10 college administrators, and we are selecting 6 in general to sit on this committee. If the formulas are worked out, the C20,3 ends up being 1,140, and the C10,3 ends up being 120. I will multiply those by the fundamental counting principle to give the numerator. And in the denominator, C30,6 ends up being 593,775. Multiplying in the numerator gives an answer of 136,800 over the denominator that I had before. This simplifies to 608 over 2,639. So that is the probability that if we randomly select 6 people, that half end up being educators and half end up being administrators. This is approximately equal to 0.2304, or in other words, about 23%. This concludes example 5.